I remember Vera as a truly gracious person, a master astronomer, and a key player in the development of the present well-established cosmological model with its mysterious non-baryonic matter. I offer an historical example. Why doesn't it want to turn? Oh, there it is. The Andromeda Nebula, optical light in the left. In the middle, the black dots are emission line regions, H2 regions. I love the story of how they were found. 1929, Walter Baade reported that the Eastman Company had given him photographic plates labeled the H-alpha special, which were sensitive enough in the red to pick up the 6600 recombination line of atomic hydrogen. That enabled him to find regions where there's concentrations of plasma that is recombining by blink comparing photographs taken in blue sensitive light and red sensitive light. He could find these things even though they're very hard to spot without that filter. Just to compare, there's how the H1 is distributed. The line and the H1 21 centimeter line both are wonderfully useful because, as Netta says, you can measure their velocity relative to the center of the galaxy. V squared over r is an acceleration. That requires mass to gravitationally bind the system. You get to find masses of galaxies. Here I've taken a set of measurements of the rotation curve of the Andromeda Nebula. Sorry?
Get the lights partly down.
We should have the lights down. You should see at the top, 1939, Horace Babcock shows in the middle circular radial velocities taken from absorption lines of stars in the bright central part of the galaxy. You may be able to see 4 large black dots. Those are H-alpha regions, that H2 regions, that for which Babcock was able to get radial velocities. Be careful with the 4 open circles, the large open circles. They are not measurements. They're the 4 measurements reflected on the assumption of axial symmetry. The main point of this is that Babcock was startled to find the very great velocities of that material relative to the center. He suggested that there may be a lot of mass out there obscured by dust. Well, that's fallen by the wayside. Or there may be a reconsideration of dynamics, and that, of course, has happened. Next step down, Mayall used Baada's positions for emission line regions, obtained radial velocities shown in the second curve. The measurements were not very precise. In places, he reported uncertainties of 100 kilometers per second, so we can't take this too literally. But we do notice an interesting sociological point. There is good evidence of a decrease in rotation velocity with increasing nuclear distance. Everyone knows that the velocities of the planets decrease with increasing distance from the sun, 1 over square root of r. Everyone knows that the mass in this galaxy is where the light is. So in the outer parts, the circular velocity should be decreasing. And of course, he saw it. There is good evidence of a decrease. I look at it, I don't see that. But then I'm conditioned to flat rotation curves. Third plot, the Dwingaloo telescope has the angular resolution to resolve 21 centimeter radial velocities as a function of position across the galaxy. The symbols are from Mayall. Somehow they don't quite match the curve above, but they're close. The solid curve is their measurement of the circular velocity. We feel a little uneasy about it. This is pioneering work. Why should I carp and complain? Except that we know, I asked them, that the small depression, you see the small rise to the right and depression to the left of the center, they put that in by hand because they knew it was so of the Milky Way. We can't judge how good a rotation curve this is. Next down, Rubin and Ford. She had 2 great advantages. First, she had Baada's emission line regions. She could then offset from known stars, from visible stars, to measure spectra. Second, she had Kent Ford's image tube intensifiers that had a marvelous effect, reducing needed exposure time to get a redshift from 20 hours to less than 1.5 hours. Here we see error flags, and we see the classic flat rotation curve with a rather abrupt transition through the center. Below that, Mort Roberts with Whitehurst used the refurbished 200-foot telescope, now long dead, to extend the rotation curve out to larger radii, and still find more evidence of Vera's that is the point that the mass in this galaxy extends beyond the light, a halo of subliminal matter. A moral from this story, I don't know why it refuses to move. Oh, no. It did move. That the presence of dark matter draped around galaxies was not a discovery. It was a realization, and it took decades. Also worthwhile to pause to consider the importance of technology. The H-alpha special. Telescopes big enough to resolve galaxies in 21 centimeter. Efficient photon detectors. In the years around 1980, I went around giving colloquia showing flat rotation curves. Vera gave me a set of 8 by 10 plastic sheets, transparent plastic sheets, showing the things you see in the middle here. They were for use in an overhead projector. That was the nadir of projection. But still, it was wonderful to have these sheets in which these rotation curves in the middle were expanded to more or less fill the sheet. It was a flat rotation curve in your face. I cannot find what I did with those sheets. I can't have thrown them out. Anyway, you get the effect. And it is true that here we have a genuine discovery. It was Rubin and Ford who discovered the universality, the near universality of flat rotation curves. There it is. I do remember my puzzling. This is Vera from an interview in 1990. My puzzling. What in the world? Why are the curves so flat? And that doesn't look like a random occurrence. She's absolutely right, of course. We're missing something. Here's an example of what we're missing. I missed this. This is a page from the American Astronomical Society list of abstracts for talks, 10-minute talks at a conference. Here is an abstract. It has the name of the authors, Rubin, Peterson, Ford. It has visiting astronomer and all that stuff. In the middle of the abstract is this figure. No room for an explanation. A wonderfully flat curve, sharp drop, a step function close to it. Remarkable, beautiful. Here again is the 1976 rotation curve. Here is a 2.2 micron image of this strange galaxy, NGC 3115. You see a distinct, looks like a disk, nice and regular. You see a bright classical bulge, and you see a stellar halo rising above it and also rising from the disk. It's an odd galaxy. Odd in particular because galaxies like this tend to be found in clusters, where it's easy to say the magic words, ram pressure stripping has removed the gas and the dust. But this is out in the field. How it got that way, and yet kept the disk, is kind of a mystery. The figure down below to the right is from Michel Capillari, who made this figure from a study by him, Romanowski, Brody, and others, of two-dimensional measurements of radial velocity and, of course, surface brightness across this galaxy, did dynamical analyses, and produced, Michel, at my request, gave me this plot showing in blue the total mass as a function of radius going out from the center. Red, the mass for a reasonable stellar mass-to-light ratio, the mass in stars. This color A trace of non-baryonic dark matter, you don't need that. It's an order of magnitude down. You should be shocked. What became of the non-baryonic matter? I mean, we shouldn't ignore this. Another shocking thing. Everyone knows that a rotationally supported disk held together by its own gravity is unstable. It will fragment first into a bar and then into chaos. This disk looks pretty stable. It's a puzzle. There are analyses of disk stability. On the left, you're reminded that the Andromeda Nebula has a pretty bright stellar bulge. That's shown as the dark, that mass distribution in that bulge is shown as the long short dash curve marked. Jerry Selwood, Wynne Evans, in an analytic and numerical analyses, demonstrated the stability of such a situation. They had a still bigger bulge, but never mind. They were willing to guarantee that the Andromeda Nebula is stable, which is good, of course. But what about NGC 3115? It doesn't seem to have any dark matter. It seems to be rotationally supported. What is it? That is a starting thing because we know disks that are rotationally supported and held together by their own gravity are unstable. Numerical simulations produce these days wonderfully good galaxies, nice spiral galaxies. They're flat and they look stable, but they have almost inevitably a bright classical bulge that, according to the theory, aids their stability. We're not surprised then, perhaps, that these disks are stable and last to the present. But here, consider this example. This is an image taken from the web. It's a stunning image, isn't it? And I hope you can see the faint traces of dust lanes running into the center and that whirlpool-like center. Wouldn't you love to see a high angular resolution image of the very center? Is there a stellar nucleus? Or maybe does that thing that looks like a whirlpool end up with a whirlpool cone? A whirlpool of stars? Well, maybe, if the stars are moving smoothly enough. What's going on in there? And what is stabilizing it? Is there perhaps a cone of dark matter that's producing the analog of a classical bulge? What's going on? Another thing I would love to see is a circular velocity measurement and velocity dispersion measurement running across the center of this galaxy. How do you account for that wonderfully disk-like appearance? Here's another example, M101. Here, the beautiful thing is, well, you notice the red H-alpha lines floating around. You notice the dust lanes running into the center. And here from John Cormandy, an HST image of the very center showing, you can see the dust lanes running right into a stellar nucleus with a luminosity a part in 10 to the 5th of the luminosity of the galaxy. Wow, what's stabilizing it? So, I now ask you to compare these pure disk galaxies with simulations. On the left, simulations by Robbie Grand and colleagues. They're a couple of years old, but I don't think the situation is going to change that much. On the right, data. The data are from John Cormandy and colleagues, Drury Bender-Cornell, and Fisher and Drury, showing distribution of bulge light to total. How much in the bulge, how much total. And one sees two elliptical galaxies that are all bulge, Mapphi 1 and Centaurus. You see this Umbraro Nebula about half bulge, half total, half bulge, half disk. You see M81, which has a substantial bulge. And over here, and a whole lot that don't have much at all in the way of a bulge. They're near pure disk. Over here, the illustration from Robbie Grand and colleagues, very sophisticated simulations, and we certainly shouldn't blame the computers for what is obtained here. They're just reporting what the physics says, and what it says is the horizontal axis is a measure of angular momentum. Vertically, the red line in the middle is equal light in disk and in total and in bulge plus stellar halo. And we see that a galaxy like M81, which has a bulge to total of about 0.3, has a disk to total of about 0.7. It's running at about the top of that distribution. All of these guys have large bulge to total ratios, small disk to total. Why are they so different from the nearby galaxies? It should be noted that, that automated measurements of bulge to total light tend to produce much larger numbers than given here for nearby galaxies. The interpretation I get from Cormany and colleagues is that that decomposition assumes an exponential distribution of light in the disk. If there's extra light in the disk near the center, it is classified as a bulge, but it's not really. It's just extra light in the disk. We are seeing a distinct difference between theory and observation, which should make us very happy. Lest I be misunderstood, I am fully convinced that the lambda CDM cosmological model is a good approximation to what happened because it fits so many tests so very well. But, well, and of course, it is excellent science for model builders to assume that model and find its consequences. We don't blame them for the result, we thank them, and we think, well, this is a little suspicious. And we should also bear in mind that although lambda CDM passes many tests, we threw that together, in fact, I threw it together in the early 80s as the simplest way to fit the observations at that time. I wasn't particularly pleased with the theory because it was so easy to do, and it was so easy to think of other ways to make a model that would pass all the tests. This model, lambda CD, with the addition of the cosmological constant, proves to be very successful. But I can't believe that it's the final answer. There's got to be more than that to our universe. And in particular, I hate the thought that the dark matter is something as simple as a gas of non-interacting particles. Got to be more interesting. Otherwise, it's just not fair. And that is why I think I so love the notion of problems. In particular, I offer then a lesson that a truly great scientist will settle questions, to be sure, but a really, really great scientist will raise more questions than they settle. They'll teach us a lot more. Thank you.
Netta.
Say that, wait,
Netta, go ahead.
wait.
The galaxy that you mentioned, 3115.
Oh, wait, Netta, maybe microphone.
So the galaxy you mentioned, 3115, that has claimed no dark matter, how far did it go? Because there are some galaxies that one still debates within the luminous radius how much dark matter one has. Maybe a little bit, maybe not so much. But how far does it go in kiloparsecs, that one?
I can't tell you that. I can remind you, remember, an effective radius contains half the light. This extends to 6.5 effective radii.
And there are stars going all the way to
Oh,
those.
oh, yes, yes. Of course. There's that very diffuse disk, goes way out.
Oh, it's a very diffuse.
Well, I mean, low surface brightness.
It's a low surface brightness galaxy.
Well, at the edges. Of course, it's very bright in the center. But then, like a dinosaur, it's bright in the middle and it's very faint toward the edges.
David?
So I get worried with these, when we get to the centers of galaxies, that these are scales at which we should not yet trust the numerical simulations. The dynamical, the stars have to be followed for hundreds of dynamical times. And I fear that I've not seen many tests done where people do things like even just start with a dynamically cooled system and let them go. So these are important problems, but we may be learning about the limitations of our simulations at this point more than new physics.
I entirely agree with that. And so I guess the basic point is we stand to learn something, maybe about the way you simulate the formation of a galaxy, maybe about the need for better cosmology. Do you find, David, that people talk much about pure disk galaxies?
Not so much.
I find that they are, well, there's that phrase, kind of hackneyed, an inconvenient truth. I think it's a wonderfully convenient truth because it's going to tell us something.
Glynis?
Could you just elaborate on your comment about the very interiors, like NGC 3110, 1300? And
Yes.
you were talking about some sort of a cone. Could you just elaborate on that?
Well,
And also the physical dimension of the region where you imagine your cone is.
yes. First, let me urge you all, Google Galaxy NGC 1300, and this image will hit you in the face, and you will look very close to the center. You will see these rings, the spirals of dust lanes. And that reminds me of a whirlpool. And a whirlpool makes me think of the cone in the center. And I think it's absolutely stupid of me to think of that, except how can you resist checking what is going on as close to the center as ever you can look?
The descent into the maelstrom.
Exactly. I sometimes use that. I'm told that in real life the maelstrom isn't nearly as fearsome as, was it Poe? Yes. But it is a maelstrom. You can see it. You can see those spirals of dust lanes. Something is going on in there.
Michael?
Perplexed by 3115. I see a flat rotation curve, and I see the light falling off.
Yeah.
And so two things come to mind. When people were resisting the idea of dark halos, they constructed these maximal disk models where they tried to use the gravitation of the disk to explain the portion of the rotation curve that was flat. And so is it just not going out far enough? It's a flat rotation curve.
Yeah, true. I should have said these are all to about the same scale. So it's only
It looks to me that the rotation curve only goes out to the edge of the light.
well, that's where the measurement went out. That measurement stops here. The new measurements stop here, twice the radius. But let me remind you of the old story. In particular, Steve Kent did a very great service. He pointed out that when you want to fit a rotation curve, you have two stellar components, a bulge and a disk. Each may be assigned a mass to light ratio. Given two free parameters, you can do a lot. In particular, he could fit flat rotation curves of many galaxies. But this, it took when 21 centimeter extended the rotation curve, that no longer became possible. But yes, in this case, except of course these people are taking the full two-dimensional measurement of the star distribution and of course of the mean Doppler shift and fitting it to a dynamical model, which doesn't seem to require dark matter.
There is very little, I'm confused about it too. There is very little light when you go from the 100 to 200.
Yes,
And the rotation curve is flat.
the rotation curve is not measured, at least I'm sure it's measured. I don't have it. This is the Rubin rotation curve measured to 100 arc seconds. These are the new measurements, not of the rotation curve, of the mass distribution. I didn't want to pester.
But how can you measure the dark matter if you don't measure the rotation?
Oh, they measured the rotation. These people, Capillari, Romanowski, Gene Brody et al., made the measurements. They published the results. I couldn't make head nor tails of it. I asked Capillari, please, do something simple, give me the mass distribution. He did it. I didn't want to pester him by asking for the rotation curve.
If you look at the light, even at 100, the light fades away.
Of course.
And the rotation curve is flat.
No, it's not. We don't know that.
No, at 100.
Oh, at 100. Okay, well, I don't know.
At 100, the light has already faded and the rotation curve is flat.
Are you questioning Rubin and Ford?
No, I'm questioning the capillary model. I just don't believe.
Well, wait. You wouldn't question the image, except, of course, we don't know the contrast.
Yeah, no.
It is saying that, yes, you're running out of light, but I don't know how much light is out here.
The image and the Rubin and Ford, I do not believe capillary. Let's make it very clear. I believe Rubin and Ford in the image. I don't believe capillary. It just is not consistent.
Because I think,
Netta, I don't think you can trust the amount of light out here at 200 arc seconds. This is an image, of course, in which you put in a contrast. How much starlight is there out there? You have to measure it.
It's much less than you see a little before, and the rotation curve is still flat at 100.
Well,
R squared is getting bigger. So
I think
since our next speaker is speaking up, perhaps it's time to thank Jim again. And